So last time we looked at permutations, where order was important. The next step is combinations, where order is not important. Sometimes order is important, and sometimes order, when we're counting different things, isn't important. So we'll start with a nice, simple example, hopefully. So this is combinations where order is not important. Alan used capital C. So instead of 10P7, he had something like 10C7. So let's have a look at this example. It's very similar to the Adam, Bruce, and Cameron, Dave, and Ed example I used before. Suppose there are 5 people in a race, and it doesn't matter where you come in that race. As if you come in the first 3, you win $50,000. So as long as you're first, second, or third, you win $50,000. So now order is not important. Adam doesn't care if he comes first, second, or third, just whether he's in the top 3. So what happens then is that if Adam comes first, Bruce comes second, and Cameron comes third, that's pretty much the same as Bruce coming first, Adam coming second, and Cameron coming third. They don't really care. The same 3 people win $50,000. So once we write out Adam, Bruce, Cameron, or A, B, C, we don't need to write A, C, B, B, C, A, B, A, C, C, A, B, C, B, A. They're all the same because order is not important. So straight away, there is going to be less. When order was important, all those things were different. Order's suddenly not important, so there's obviously going to be less. So let's try to list them again. So let's assume, starting down here, that Adam and Bruce are in the top 3. So Adam and Bruce are in the top 3. So the only other way to finish that top 3 is Cameron, Dave, or Ed. And that's it. Let's suppose Adam and Cameron are finish in the top 2. We don't need to write Bruce here. He's already been done over here, Adam, Bruce, and Cameron. So Adam and Cameron, there's only 2 left. Dave, Adam, Cameron, Ed. And again, if Adam and Dave are in the top 2 or in the top 3, if they are 2 of the 3 people, then you don't have to write Adam, Dave, and Bruce. It's here. You don't have to write Adam, Dave, and Cameron. It's here. So the only one left is Adam, Dave, and Ed. And suddenly there is a lot less. And if you are listing them, combinations tend to give you this triangle all the time. You always get this triangle. Permutations give you a rectangle, and combinations give you this triangle where there's always one less. So that's all the ones where Bruce is in the top 3. Let's look at if Bruce and Cameron are in the top 2, but we don't need to write Adam here. That's it there. Bruce, Cameron, and Adam. So the only ones if Bruce and Cameron are in the top 2 is Bruce, Cameron, Dave, Bruce, Cameron, Ed. And then Bruce and Dave and Ed. We don't have to write anymore. And again, you get this nice simple triangle. And the last one, if we look at Cameron and Dave in the top 3, so we've already got 2 of them, Cameron and Dave. We don't need to count Bruce. We don't need to count Adam. They're already covered over here. So if Cameron and Dave are in the top 3, then the only other way we can do it is Cameron, Dave, and Ed. So suddenly there is a lot less. And if we count them all up, there should be 10. So instead of 60 different ways, when we did permutations and order was important, there are only 10 different combinations when order is not important. So how do we go from 60 to 10? Or why did we divide by 6? Because that's really what we've done. To get from 60 to 10, we've divided by 6. Why we've done that is because there are 6 different ways A, B, C can be sorted. Adam, Bruce, Cameron in permutations was written Adam, Bruce, Cameron, or Adam, Cameron, Bruce, or Bruce, Adam, Cameron, or Bruce, Cameron, Adam, or Cameron, Adam, Bruce, Cameron, Bruce, Adam. But now they're all the same, and there are 6 different ways, so we divide by 6. How do we get 6? Well, 6 is 3 factorial. 3 times 2 times 1. Example 2. In how many ways can you choose 5 people from a larger group of 9? So if order was important, it'd be 9p5. So 9 factorial over 9 minus 5 factorial. But the 5 people you select can be selected in 5 different ways, or 5 factorial different ways. So instead of just 9p5, we have to do 9p5 divided by 5 factorial. And this is the definition of 9c5. Okay, this is the definition of 9c5. So 9c5 is 9 factorial over 9 minus 5 factorial. That is just 9p5. Order is important, 9p5, and then we just divide it by 5 factorial. If it's nck, n factorial over n minus k factorial divided by k factorial again. So let's look at a few more examples perhaps. If there are 9 people in a competition where first gets 2,000, second gets 1,000, third gets 500, and fourth gets 100, in how many ways can the 9 people fill the first 4 spots? So here order is important. I'd prefer to come first compared to fourth. So we are selecting 4 people from 9 and order is important. How many ways can we select the first? 9. Second, 8. Third, 7. Fourth, 6. Therefore, 9 times 8 times 7 times 6. This is down here as well. 9 factorial divided by 9 minus 4 factorial. And that's what 9p4 is. Suddenly, order was important. Let's make order not important. If there are 9 people in the competition where the best 4 people all win $800, in how many ways can the 9 people fill the 4 spots? If order was important, it's 9 times 8 times 7 times 6. But in this case, order is not important. So let's look down here. If the 7th person comes first and the 3rd person comes second and 4, then 1, all of these are the same and many, many more. So 7, 3, 4, 1, 1, 3, 7, 4, 3, 1, 4, 7, 4, 1. They are all the same. How many ways could we write this? Well, there are 4 ways to arrange the first person, 3 ways the second number, 2 ways, and then 1 way. So 4 times 3 times 2 times 1. So we have to divide this, the 9p4, divided by 4 factorial. So it becomes 9 times 8 times 7 times 6 divided by the 4 times 3 times 2 times 1. And that's what 9c4 is. So hopefully that gives you a little bit more of an understanding of the difference between permutations and combinations, and a little bit of an insight into the formulas that Alan was using. Thanks. That wasn't so good.